Hey everybody, in my earlier video, which I will link to in the description, I was talking about permutations and I described the notion that permutations can be generated from just a bunch of transpositions of two elements from a list. So for example, if you start with the original permutation 1, 2, 3, 4, and you want to generate the other 23 permutations of that, then you can just apply these transpositions on the permutation, on the original permutation to get a new permutation. So for example, if I apply the transposition of 1 and 2, 1, 2, 3, 4, I'm going to switch the elements 1 and 2 in the permutation to get 2, 1, 3, 4. And in the earlier video, I did this with a breadth first search. So basically, I was kind of smart about how I generated all 24 permutations. Basically, I started with the first permutation, generated all of its neighbors, and then once I had these other 6 permutations, I generated their nearby neighbors using these transpositions, like switching 1 and 2, or down here switching 1 and 3. But in this video, I'm going to explore the concept that we do kind of more of a brute force approach. And this is going to lead to a pretty important observation that I'm going to leave you hanging on. But in our brute search implementation of finding permutations, we're going to have these transpositions and we're going to do a 4-way nested loop where we take our original permutation and we're going to find its immediate neighbor for all transpositions P among transpositions, and we're going to append that to a dictionary that records all of the tuples that led to the creation of the permutation. And we're going to loop over Q and do similar things, similar for R, similar for S. I don't expect you to completely understand this code, but the name is correct. It's like a very brute search way of creating a list of permutations. But when you run this code, you get an output like this. So we have the starting permutation that is just, the integers 1, 2, 3, 4 in the most natural order. And then in my output, I'm showing you basically what happens as a result of this function executing and creating this permdict, which I list out here in this loop, and I do a little bit of sorting and aggregate. Aggregate means probably the wrong word, but so in order to get the permutation 1, 2, 3, 4 from the original permutation, the most obvious thing to do is apply literally 0 transpositions, which of course just keeps it the same. But you can also, there are also these 6 different ways to apply 2 permutations. And of course here, what I'm doing here is in my brute force search to find all the permutations of 1, 2, 3, 4, I just literally have this quadruply nested loop to create 4 different transpositions that I'll apply the permutation. So when I apply the transposition 1, 2, and then apply that again, well, switching 1 and 2 and then switching 2 and 1 just brings us back to the original permutation. And of course that applies for 1, 3, 1, 4, 2, 3, all of these are just doing the same things. And then it gets a little more absurd where, like, for example, you could do the permutation 1 and 2, and then 1 and 2, and then 1 and 2, and then 1 and 2. And of course you're back to the same thing. But I want you to observe that the number of transpositions that I did to come back to the original permutation here are all even numbers. You can see there's many ways to do it with four transpositions, but like normally, I mean, not normally, every time you'll see that the transpositions include this sort of aspect of redundancy. So, like, in order to go from 1, 2, 3, 4 back to 1, 2, 3, 4, I can switch 3 and 4, switch 3 and 4 back, then I can switch 2 and 4, and then switch 2 and 4 back. Now, in order to go from 1, 2, 3, 4 to 1, 2, 4, 3, you can see that the most direct way to do it is to make one transposition where I simply switch the elements 3 and 4. And again, if you go back to my earlier video when I was doing a breadth first search, I would get to these like shortest combination of or shortest length of transpositions in an efficient way. But in this code, I'm doing a very brute search way, and I'm not trying to kind of like prune my search tree. But you can see here that in order to go from 1, 2, 3, 4 to 1, 2, 4, 3, the most efficient way is just obviously to switch the elements 3 and 4. But I can also do these things like I can switch the elements 1 and 2, and then I can switch the elements 1 and 2 back with each other, and then I can make the swap 3 and 4. I can also do it by switching the elements 1 and 2, leaving those alone for a second, switching the elements 3 and 4, and then swapping back the elements 1 and 2. And again, here I want you to observe that even though there are all these like kind of redundant ways to do transpositions, the number of transpositions in every instance is an odd number. And again, you can see 1, 3, 2, 4 is basically similar to the prior example. The most efficient way to get from 1, 2, 3, 4 to 1, 3, 2, 4 is to merely swap the elements 2 and 3. But of course, you could swap the elements 1 and 2, and then swap them back, and then swap the elements 2 and 3. And that would achieve the same effect. And then you can get into this other permutation where it is apparently impossible to achieve the permutation 1, 3, 4, 2 from 1, 2, 3, 4. It's impossible to do that unless you do at least 2 transpositions. So you could swap the elements 2 and 3 and then swap the elements 2 and 4, or you could swap the elements 2 and 4, then swap the elements 3 and 4, or you could swap the elements 3 and 4 and then swap the elements 2 and 3. And in some ways, like all three of these are the most direct way to do it. But then there are also all these ways to achieve the same permutation with 4 swaps. And again, you'll see like some of these include some rather ridiculous redundancy. Like I could swap the elements 1 and 2 and then swap them right back. So again, it's the same thing. I swap, right back to the same place. And then I do 2, 3, 2, 4. So essentially this line here is just a more complicated way of doing that. But if you go on down the line, you will see that every permutation can be achieved by a whole different way of doing transpositions. There's usually, I showed you an example where there are 3 kind of equivalent transposition or tuples of transpositions that would get you there. You know, often there's like one obvious single transposition that will get you to the permutation, and then there are all these kind of redundant ways of doing it. Here's another example where in order to get from 1, 2, 3, 4 to 2, 1, 4, 3, you can transpose 1 and 2, then transpose 3 and 4, or you can transpose 3, 4, then transpose 1 and 2. And you can probably understand pretty quickly why doing those in either order achieves the same effect. But then you notice all of the ways that you can get to that permutation by making 4 transpositions. But again, I want to emphasize that in this particular permutation, you can only get to it by an even number of transpositions. This one, you can only get to it by an even number of transpositions. This one, you can only get to by an odd number of transpositions. And this is a particularly interesting case where you can only get to it by exactly 3 transpositions in the context of the way that I wrote the code, where I didn't attempt more than 4 transpositions. Obviously, you could achieve this with 5 transpositions by doing these 3 transpositions, and then just transpose 1 and 2, transpose them back again. And you could do it with 7 by, do, and, go up to 9 and 11 and so on and so forth. But there are always an odd number of transpositions that lead to the creation of this particular permutation. Here we have another example of all odds. Here we have another example of all evens. All even, all odd. And what my program demonstrates, and I believe my program to be correct. What my program demonstrates but doesn't necessarily prove is that any permutation has a certain parity associated with it. Any permutation can either be arrived to by an even number of transpositions or an odd number of transpositions, but it is impossible to reach a permutation by both an even number of transpositions and an odd number of transpositions. And that's like a really important fact in abstract algebra. And you can, in fact, prove it using mathematical reasoning. But I hope that this program gives you some intuition of why that's the case. And I think it's useful to use a programming language like Python to confirm your intuition about something and to prove it. Especially, permutations can get really large. But if you're dealing with permutations over a set of like 4 or 5 integers, then you can kind of do an exhaustive search over some space of transpositions that you're trying to generate. And I think this is a perfect example of how Python can confirm your mathematical intuition about something. I hope you found this interesting. Thank you for listening.